In this video, I'm going to discuss about the technique known as vectorizations. So let me first introduce to you what is vectorizations and how do we perform vectorizations and what do we really achieve by performing vectorization. Vectorization is nothing but the process of converting loop-based operation to vector operations. So what do we mean by that? So let's take an example here. So the example is like this. We have a series of numbers and we represent in an array. So the array is having 5 numbers 2, 3, 4, 5, 6, and we want to add the index number to each element. So what do we mean by index number? So 2 is the first element, so we want to add 1 with 2. 3 is the second element, so we want to add 2 there, and so on. So we want to add the index there. So how do we do that? So generally by taking a loop, we can perform the task by adding the index number to the elements. So we have got 5 numbers, so we will use a do loop I equal to 1 to 5, and each element will be added based on the index. So if we can index it, okay, so slight change in the code. Okay, now it's correct. So AI, so I is the index equal to the previous number. So here in this case 2 plus 1. Similarly, the next loop will have 3 and then 4, 5, and each will be added with their corresponding index value, right? Now that's by using loop. We can vectorize this code and make it more efficient. So that instead of 5 times of loop, we can do it in one go, and by which we can also achieve higher efficiency. Okay, that will take much less time. So how do we do that? We do that using matrix programming. So what we do is, so we have this array over here A. So we keep it in a matrix, and we create another matrix which will have the index number. Now we create I as the index matrix, which has got values from 1 to 5. So these are the index numbers, index values, and the matrix A, which will have the numbers 2, 3, 4, 5, 6. So A will have 2, 3, 4, 5, 6. So the numbers in the array will keep it in a matrix. Now instead of looping, we can just simply do a matrix addition, and we can achieve the same thing that we have done in the previous step. So how do we do that? We simply add the matrix A and I, and we'll get a transform form of matrix where each element is added to the corresponding index number. Now this is much more efficient than the looping construct. And let's see a little more complicated problem and see what's the difference in time in SAS. So the problem statement here is that we have a data set which is having 1 lakh rows and 100 columns, and the values in each of these data points are probabilities ranging from 0 to 1, and we want to make it binary. So the probability values are continuous in nature. We want to make it binary, and based on the criteria, if it's less than 0.5, then we want to make the value as 0, else it's 1. Okay, so how do we do this? Well, even before we start with doing it, we'll create a data set which is a 1 lakh rows with 100 column data set having probabilities value from 0 to 1. So I have used the random sampling from the uniform distribution, which gives you the data set from random distributions. So let's first see the data set. So we will use proc IML Let me show you the data set first. It will be much easier for you to understand. So let me take a smaller sample, otherwise it's going to take a lot of time to print. Okay, so now I'm creating an uniform random sample from uniform distribution with 100 columns and 100 rows, and I'm printing it. You will see it in the output. Okay, as you can see, this is the kind of matrix that we are going to have. Now that will be much bigger matrix because we have got 1 lakh rows. I have taken a smaller sample which is 100. So you can see all places you will have numbers between 0 to 1. So anything less than 0.5 we will make it as 0, and anything greater than 0.5 will make it as greater than equal to 0.5 will make it as 1. So we'll proc IML in SAS. So this is how we do it. Now first we create a matrix which will have 1 lakh rows and 100 columns, each having a numbers between 0 to 1, and we create a do loop which is going to have okay, let us do it for 1000, otherwise it's going to take a lot of time. So 1000 rows and 100 columns. Okay. Now the syntax is simple. We use two do loops, one for the rows and the other one for the columns. There are 1000 rows, so I equal to 1000, 1 to 1000, and then j is from 1 to 100, right? The usual do loop with a two-dimensional representation. So if xij is less than 0.5, then xij is 0. It's a very simple code. Else, if xij greater than 0.5, then its xij is 1. Okay, you don't need to write it. You can simply write else. That's also going to work. Right, so it's a simple notation. Anyone comfortable with the do loop will understand this very well. That based on the condition whether it's less than 0.5 or greater than, we are simply transforming the variables into a binary variable 0, 1, 1, and the index for this variable is I and j, which varies from I varies from 1 to 1000 and j varies from 1 to 100, right? Now let us run this and let us see how much time does it take, and we'll then convert it into a vectorized form and see what's the time taken. Something is wrong. Okay, so it takes 0.35 seconds. So that's what it takes, right? So now let's vectorize this. Okay, so how do we do the vectorization? We'll create a similar sample from uniform distribution, and we'll use a function in proc IML which is LOC, which finds out the location of a particular number. Okay, and automatically we can actually replace the continuous numbers into binary numbers based on the condition. Okay, so now what's the difference here? So the difference is that in the previous case we were doing one by one. Okay, so the loop takes one at a time and do the transformation and go to the next one after the first one is done, right? Whereas here in this case we are using a function LOC, which gets the location of each number or each element in the matrix, and it is performing the transformation for all the elements in the matrix at the same time. So the LOC function in IML is helping you out to get the location, and the transformation is happening at the same time, right? So that's the main difference between your vectorized code and the non-vectorized code or loop-based code. Here you don't need a loop. So the entire location or the index of your elements are now coming in the form of vector. So instead of looping I and j through 1000 and 100 times, you can just keep the location part in a matrix and use the matrix to do the transformation. So it's happening internally and it's not shown to us, but this is the way we write the vectorized code. So x is the matrix, LOC the functions, and within bracket we use x minus 0.5. So that means any places where x is less than 0.5 will get their location, okay, and we'll get a matrix, okay, which will have yes or no. If this condition is satisfied, then we'll replace every number satisfying this condition with 0. Similarly, we'll perform the second kind of transformation, whereas the values are greater than 0.5. So a simple function is able to do the entire transformation in one go. So that's the main advantage of having a vectorized version of code. So let us run this and let's see how much time it takes. Well, it takes 0.2 and the CPU time at 0.09. In the earlier case, the CPU time was 0.32, and you can see the difference in the computation time. So it's 0.09 here, and in the first case it was 0.32. So the code performance can well be increased or improved by using vectorizations. If the data size increases, say for example we have 1 million rows and thousands or 10,000 variables, there will be a significant amount of difference in the computation times. So that's why it's very useful.